Downtown. So here we've got some wind and current word problems. So these are pretty similar to the distance, rate, time problems that we already did. The difference in these is that you're either moving through water or through air. So the wind speed or the current speed can affect your rate. So on number 1, we've got Garth can row 5 miles per hour in still water. So basically, if the water was not moving at all, he would go 5 miles an hour. It takes him as long to row 4 miles upstream. So like if your stream is moving that way, upstream means like this. So you're moving against the current. So the current is fighting you, which makes you move slower. So it takes him as long to row 4 miles upstream as 16 miles downstream. And downstream, of course, would mean you're going with the current the same way, you're moving the same way the water's moving. So it's helping you along. It's actually making you move faster. And how fast is the current? So you want to set up your distance, rate, time problem, your chart. We have upstream against the current, so the water is working against you. Downstream is with the current, so the water is helping you move along. And he's going 4 miles upstream, 16 miles downstream, and the times are equal. All right, so in this case, we've got time upstream equals time downstream. So I'm still going to set up distance over rate. So 4 over 5 minus c. Let's talk about this. So when you are moving against the current, you're going to take your speed in still water or in still air, like how fast you're actually trying to go, and subtract the speed of the current because it's working against you. So it's going to make you move slower at a lower speed. Whereas when you're going downstream or with the current, you can take your speed, what you're trying to go, you're trying to go 5 miles an hour, and add the speed of the current because it's helping you move along faster. You're going at a greater speed. So upstream or against the current is going to be subtracting. Downstream with the current is going to be adding. Anyway, so upstream, 4 over 5 minus c. Downstream is 16 over 5 plus c. And now, since we've got fraction equals fraction, we can take a little bit of a shortcut and cross multiply, which is the same as getting a common denominator, gives you the same result. So I have 4 times 5 is 20. 4 times c is 4c equals 16 times 5 is 80. And negative c, so minus, times 16 is minus 16c. Then I have to cancel one of the c's, and I'm going to choose to cancel the negative one. So I have 20 plus 20c equals 80. Oops. That's weird. Try that again. 80. And I'm almost there. I need to subtract 20 and then divide by 20. So I'm going to go over here. So I have 20c equals 60. Divide by 20. C equals 3. So the current goes 3 miles an hour. All right, let's look at number 2. Kind of a similar problem, although if you look at the table, you'll notice that we know the speed of the current this time, and we're trying to find the speed of the boat in still water. So we're trying to figure out how fast the boat is trying to go. So a boat goes 240 miles downstream, so downstream here, in the same time, so these are equal, that it can go 160 miles upstream. So we have downstream, time downstream equals time upstream. And the speed of the current is 5 miles an hour. So notice I'm taking the speed of the boat in still water. So how fast is the boat trying to go? And when I'm fighting the current, I'm subtracting the speed of the current, which is 5 miles an hour. When I'm going downstream with the current's helping me. I'll take the speed I'm trying to go, add the speed of the current, and that'll give me how fast the boat's actually going through the water. So downstream, 240 over r plus 5 equals 160 over r minus 5. And again, I'm going to cross multiply. So 240 r, and then minus 5 times 240, 1200, equals, so r times 160 plus 160 times 5. And then I'm just going to kind of solve it like before. I need to cancel one of the variables on one side. So I'm going to cancel this one. And then I need to add the 1200. So I'm actually going to do that in one step. So subtract 160r to cancel it. And I'm also going to add 1200. So basically I'm doing in one step what took me 2 steps up here. I'm just putting it all together. So I get 80r, that got canceled, equals 2000 divided by 80. So when I divide this, I get that r equals 25. So that means this boat is trying to go 25 miles an hour. And for part of the time, the current is fighting against it and making it go only 20. Whereas the rest of the way, the current is helping it along and actually making it go 30 miles an hour. So the other variation you've got on this is a plane of some kind or other airborne vehicle, or even a bicycle, that's fighting against wind. So headwind means you're going against the wind. So like if this is your little plane, oh God, let me see if I can draw a plane. Isn't that a beautiful plane? Not really. It's kind of a bad plane, but that's all right. You know what I mean? So headwind means the wind is hitting you this way, running up against you. So you're going to take your speed in still air, so the speed you're trying to go, and subtract the wind speed because it's making you go slower. Whereas tailwind means the wind is actually hitting the tail of the plane, so it's helping the plane along. So you're going to take your speed in still air, so the speed you're trying to go, and add the wind speed because it's helping you go faster. Otherwise, mathematically, there's no difference. It's still the same process as you did up here with the water. It's just the vocabulary. You have to know what headwind and tailwind mean. So. Go ahead and try some of these examples yourself. If it is Thursday and you're working ahead, let me know if you need help. If it is Friday or after Friday, then go ahead and ask me if you need some help. We're going to do some in class together. So, thank you very much.